into rockfall mitigation. Rockfall mitigation for us, not always, but very often then deals with these rockfall barriers, which you can see here. I believe that briefly you are familiar with this concept of having posts being anchored with bolts to the subsurface. And then there will be like a top support rope and a bottom support rope where actually the mesh panels are carried on. And on the lateral parts of the barrier, you can see here some braking elements, which are also anchored into the subsurface, that in case of an impact, like you can see it here on the right-hand side, the deflection of the mesh and then consequently the pull on these support ropes will dissipate it through these brake elements into the subsurface. But before that, longhand, before that, we have to address what is rockfall, respectively, what are the necessary parameters which we need to assess or have a better idea of to come up with a proper solution. That means to get an idea of what is the energy of the rockfall and what is the bouncing height along a trajectory, especially at the selected barrier solution, because the bouncing height and the kinetic energy at this very point, for example, will determine the choice of which barrier we can propose to address the problem. So going back, so now before we look at it into detail, we have a source zone. We need to identify a trajectory, and of course there must be some asset, some infrastructure which we want to protect, and usually we have some sort of catchment or a deposition zone. So if we look at this a little bit more in detail, the identification of the source zone, of the location, and also its size, excuse me, is quite essential in this process. Because if we determine the wrong location, which then will determine maybe in the wrong height, will give us at the end a wrong energy content of the possible rockfall. Also, of course, the definition of the boulder size, and also then what we will later see, the geometry will rule the dimensioning process, because of we are well aware that the bigger size boulder in the end will relate in higher energies. The triggering mechanisms are also quite important to understand. Of course, frost most likely in Malaysia will not play a role at all. But for sure, rainfalls are one triggering mechanism which we have to deal with, especially in Malaysia. Also, earthquakes can be, and construction blasting is also something which we need to take into account, especially when we talk about alignments, where for new alignments or in the past for the alignment, blasting has been carried out to a big extent. On the boulder trajectory, we need to know, or we need to understand the topography. We need to understand what are the ground conditions, because what can easily be imagined, and what we will see later also, is that rocks hitting a bedrock surface on their trajectory will vary or will behave differently, rather than the rock will hit a talus area or a densely vegetated area with forests or other vegetation. So here, this is actually to illustrate what are the difficulties, and I will come back to that again and again, to determine the trajectory. because until very lately, what we usually did would have been 2D rockfall simulations, and it's also only in the last, I would say, 5, 6 years that it gets more and more common that actually we would carry out 3D rockfall simulations to have a better understanding of the trajectory and how the rock will move on the slopes, and taking into account the topography of the slope. Because here, if I just define a linear 2D rockfall trajectory, it's quite obvious that it simplifies the model to an extent that we have to be aware of what actually is at the end of the day the meaning of the result. Catchment zone, so nearby the asset which we want to protect, we need to be aware about space conditions, what is there. For example, we need to be aware of installation and maintenance, which in this case, so close to the road, is probably not a big issue. But if we imagine the barrier would have been put up that ridge here, it still doesn't look that difficult, but we will see examples where it becomes quite a challenge for the installation. And of course, then consequently also for the maintenance, because as we can see here, I mean, these barriers then need to be cleaned. The debris has to be taken out. There must be a visual inspection on the barrier if certain components might be replaced or not. Additional information is impact marks. That's what it says here, or we call silent witnesses. So, for example, very often when I come to a new project, I would watch the road surface first to see whether there are impact marks from the past, or I would watch down the slope first before I look up to see blocks, or have an idea of the block sizes which could be found there from previous events. And with that help, then we could go and also do a back calculation to have a better understanding of the site condition and the possible rockfall incidents and energies happening there. So as a summary, on these rockfall characteristics or decisive important input parameters, we can say we need to have an idea of the boulder size and geometry. We need to have an idea of the cross section and of the possible trajectory. And you can see here in this 3D simulation that if we would have done this as a 2D model, where would we have put actually the trajectory? Maybe like this, or maybe like this. So these are the important parameters: slope geometry, geology, then ruling a little bit the rock size and geometry. And not going into detail, I have a couple of presentations, slides here from the WSL and the SLF. These are the main research bodies or governmental research institutes for natural hazards in Switzerland. And just in the last, I would say 5-6 years, they have been looking intensively into the improvement of those simulation programs to include more parameter which can make or will make in the future the results of rockfall simulations much more accurate, even though they are still models. So some of the parameters of interest, is a repetition I told you before already, will be, of course, the trajectory, then in a 3D model, there come all these implications of the 3D coordinates, which will eventually rule the translational, but also the rotational velocity of a rock, will rule the jump heights and the lengths, and then consequently, of course, the energy of a rock fall. I believe this is more or less, yeah, the fundamental problem is really finding a correct relationship between incoming and outgoing energy or velocity at contact points along the trajectory. And in the next slide here, we can see a little bit that most of the times when we deal with the 2D Rockfall simulations, we would assume point mass, or very often we would just assume this sphere-like shape, which in reality, of course, is something different than when do we have those sphere-like shapes? Hardly ever in reality. So here I show you a short video. Just have to get off this one. This is actually, this video has been done through a test series, which we carried out together with the WSL. So we went on a natural site. We used different shapes and different size of boulders, which were equipped with lots of sensors. So the WSL and SLF, they could learn about the movement of the boulders in a natural environment, and which we don't see in that video, at the lower part, at the foot of the slope, we put the rockfall barriers because we wanted to see eccentric impact in the barrier, or more natural like impact in the barrier, rather than in the artificial test setup, how barriers until now are tested in a quarry, where you actually shoot in the middle of a field, which is not the case in reality. So we have a quick look at this video, and I hope you can see it a little bit, and just try to see how this boulder moves on the slope, and yet now will change its direction and comes towards us, and then again accelerates, the rotational velocity increases, and we have one incident here. Yeah, so you have seen probably that the boulder hit this very small rock outcrop and completely changed its way. And also the cameraman, we will see now, the cameraman lost the boulder because it was quite unexpected. So hits this part of rock and up it went, and it's out of the picture. And then now only we can see here that he catches it, and afterwards he can't find it anymore until it ends and stops in the slope. So this is to illustrate or make us aware that the movements can be quite unpredictable. And I have another nice video to illustrate this. And that was a coincidence, of course, that this rockfall was recorded, and the source is somewhere up there, here on the right-hand side. Can you see my pointer? I hope so.
Yes.
Okay, good. Yes. And so the video only starts, or we catch only the situation once the rocks are down here. And what is quite surprising, that we have some rocks going here on the right-hand side, and we have other rocks which will go in a totally different direction. Well, not totally, I mean, they follow gravity down the slope, but also these rocks over there, they stopped, whereas that other one here is going down further down the slope now here, redirecting its trajectory, going more than if we look upslope to the left-hand side, and then eventually stops somewhere down here in the forest. And with this new approach of the WSL to improve 3D simulations, they've been introducing these in RAMS. RAMS is one of the famous 3D simulation, Rockfall simulation programs. And before we have a look how then the back calculation, the back simulation looked like, the source zone was, let me just change here this again. The source zone was here, so it was the same source zone of these two rocks. And you can see one went here on the right-hand side where it stopped, because the terrain was not that steep anymore than on the other side. And the other one went all the way down here, and then later on even more to the right. And they have been simulating this now with RAMs, taking into account the small scale topography and also the geometry of the boulders, and quite promising results from that. You can see here the release of the boulders from that source zone. And also here in the model now we can see some rocks go here on the left-hand side and eventually stop, whereas others take the path here on the right-hand side, and then only one or two go down here, where actually we have seen in the real event the boulder stopped. So I believe that this kind of 3D rockfall simulations will be the future. Meanwhile, I mean, with the help of drone flights, it's relatively easy to obtain a point cloud, a 3D model from possible slope sites. With the help of LiDAR also, or LiDAR, we can reduce or neglect the vegetation effects to have a more accurate result in the rockfall simulation. So change my pointer here again. And then we jump into some projects. The first project here from India, in the federal state of Maharashtra. I have brought you again a video. I hope that the quality for you guys will be fine. So we can see here a project where we have been installing a couple of rockfall barriers in the last 3 years, also including a 10,000 kilojoule barrier. Here, the trajectories are more or have been more easy, I would say, to determine because of the sheer steepness of the terrain. So here we only did 2-dimensional rockfall simulations to determine the maximum energies, and then come up consequently with the design of different barrier lines of different energy and different jumping heights. You can see here during the installation that the posts have been brought up with a crane. Fortunately, in India, they have big enough cranes to reach that height, because it's still something like 50, 60 meter height above the road level where the installation has been executed in some places. You can see here some of the assembly. Just wait until this properly finishes. And you can see it's quite recent. The 10,000 kilojoule barrier was just installed last year. Another project which I would like to show to you is this Vaishnu Devi shrine project, which is located here in the upper north of India. That Vaishnu Devi shrine is one of the huge or most important pilgrimage places for Hindus, and they have something like 11 million visitors per year. And all these pilgrims will walk the path, which we will now see on the next couple of slides, which is in total, I believe, if I'm not mistaken, something like almost 10 kilometers up to the shrine location. And in the past, you could see there's frequent rockfall here. They have been protected by this metal shed roofs, which of course cannot resist bigger impacts or bigger energies. And from time to time, they had severely injured people and also casualties. And the solution he proposed here on the left-hand side, don't sit here. Yes, of course, the more time you will remain in that area, the higher will be the risk that you are going to be hit. But that can't be a solution for, not in the 21st century, I would say. So you can see here this metal roof. And on that picture, you can see here on the left-hand side, that is the shrine location. And you can see here again, this is the pilgrim path. And in that project, we have been initially approached by the authorities of this shrine, so the religious authorities, and it took like something like 3 years to develop and refine mitigation measures for the site, until then in the end they agreed and installation was carried out, which you can see here. Couple of pictures during the post erection. Very challenging environment to install. Some of the barriers which have been further upslope had to be carried in 1 or 2 places by hand. This is not the one. I believe here they have been reaching. They have been reaching by helicopter, and in other places, which we will see in the next picture, I believe. I want to point out. Yes, I want to point out this. You can see the post is actually been coming to the site in 2 parts. So somehow they could actually handle it to get it there, because I mean, this whole post is probably almost a ton. So very challenging installation environment for this project. Also, have a look at this here, which is not really a rockfall. We can judge from the size, so it's more a slide of materials, or might have even been a small debris flow being washed from this channel into that barrier. So this is after the completion of the project. You can also see here the pilgrimage path, and then here on top again. So there are certain serpentines going up all this mountain. You can see here also some rock face which has been covered with the mesh solution instead of a barrier solution, and then here a couple of barrier lines. Also here a picture during construction. And I believe these are the last 2 pictures on this project.